being negative. Okay, what it consists of is a bolt, and what is this? What's the significance of this serrated end? Remember? Okay, anyone know? Okay, you get a machine. Okay. Yes, exactly. Okay. What happens is that the installation equipment will grab onto this shank and hold it and turn the nut against the shank. Okay? In fact, on a Lejeune fastener, this head is not a hex head, it is a carriage head. Okay? Smooth, round, you can't hold on to it, right? The intent there is to get the twist off to occur at the stage where the bolt is properly tightened, right? Okay? So one person instead of two, okay? You have to get the metallurgy right so that it twists off at the right time, okay? If you get dirt or corrosion of any kind going on between the nut and the shaft in the threads, it will twist off early, okay? The carriage head is there so you can't remove it once it's been installed and the end is twisted off. You can't fit it. I mean, it will rotate in the hole as opposed to the nut come off. So you have to get the torch out to actually remove it. That's the quality control. Does that make sense? Okay, downside to this is you can't remove it without the torch and damaging whatever surfaces you've got. You can't get the metallurgy right to be able to twist that end off with any degree of consistency if the bolt is larger than 1 1/8 inches in diameter. Okay, shank. Okay? So, if you have tension critical bolts, what are the other options that we have to install a bolt that is tension critical in a connection? Yeah.
Torque wrench.
Excuse me?
Torque wrench.
Torque wrench. Okay? We torque it, right? And we have to go on site and get that torque right, so that in fact the torque gives us the tension. It's a translation, isn't it? Between the torque, just like the twist off end is a translation. What we're really looking for is tension in the bolt, and we're translating torque into tension, right? Which has with it variability depending, again, on the friction between the surfaces, which can be degraded by rust, by dirt, by moisture, okay? Any other options to install a tension critical bolt? There's a thing called the turn of the nut method. What does that involve? Okay? Very good. Okay, you're going to determine the length of the bolt that needs to be tightened, right? And you're going to say, okay, I'm going to tighten this down until I get the surfaces that are so that they're together. Okay? At which time I'm going to turn this nut, or I'm going to mark it with a piece of paint or something permanent, right? Relatively permanent. And I'm going to rotate it an additional third of a turn, half a turn, whatever it takes for the given dimension to be able to properly tighten it. Okay? But you've got to make sure that this end doesn't turn at the same time that you're turning this end, right? And you've got to be very careful you don't overturn it. You can break the bolt and so forth, right? Okay, so we got a team, I led a team of skill and stakeholders together. Oh, there's a fourth method actually. It's called a direct tension indicating washer. What is that? DTI. You ever heard of that? Okay, if you look at this washer right here, you can look, and I'll pass these around in a minute, but if you look at that, it's got some dimples in the end of it. Okay? Those dimples are specifically designed so that as you tension the bolt, they squish. When the dimension between that and the washer is sufficiently reduced, that's a direct indication of the tension in the bolt. That make sense? Okay, so cost is involved in the cost of the material. the cost of the equipment, how long it takes you to do the installation, whether you can do it with large bolts, okay? It essentially takes the same amount of time to install a large bolt as it does a smaller bolt. So if you can use less larger bolts, it's going to be cheaper, okay? So all of that comes into play. Now, we got a team together that we facilitated the introduction of lean principles, such as I have noted here as various types of disciplines, okay? And we said, okay, there's another couple of things we want to deal with. That end that twists off, if you're not careful as an installer, can go bounding down through the structure and hit somebody on the head, right? So we don't want that to happen. So let's get rid of two things at once, okay? Let's say we change the metallurgy, so we had to have the technologist there from the manufacturer that could tell us whether we could change the metallurgy so that the end does not twist off, okay? That enabled us to go as large a bolt as we wanted. We're no longer limited to 1 1/8 inches. We can go 3 inches if we want. Okay? The second thing is we came up with a scheme that would introduce into the area, the space below the dimple, some caulk, specially designed caulk in a pathway, so that when those dimples were properly depressed, it would physically squirt outside of the installing device, and you could see, the installer could see it was properly tensioned. Okay? So with those two changes, we fundamentally changed a bolt type that had not been improved for 25 years. Significant. Guess what the estimated sales increase was? $600 million a year. The salesman that introduced these to project managers on the site where they're doing large steel erection with tension critical bolts were reported it didn't come across the table at the guy because of the productivity improvement of that analysis. That's the kind of thing that we're talking about being able to do with these lean principles. You get the right team together, you lay on the table the technology and the limits of that technology. You say, okay, well, what could we do to retain everything we want and overcome the things we don't want? You begin to ask the difficult questions and you come up with solutions. You implement them and you have a significant improvement in the industry. Okay, let's take another look at a system. Okay, this is called the Heyman Igloo. It was designed by, can you see that? Yeah. It was designed by the U.S. Air Force with the intent of being able to counteract the problem that Air Force bases have, that they're being encroached on right up to the end fence by neighborhoods. And they store conventional munitions on these Air Force bases, okay? So they came up with this igloo design. This is just one segment of it. It'd be 27 feet, well, it's about, I remember now, 125 feet long and maybe 27 feet wide and about, what, 14 feet high, something like that in dimension. Okay, and the idea was to store the conventional munitions in these underground igloos. They have a blast door on the front. They load them with munitional bombs, basically, okay? And they set them sufficiently apart that if they get an explosion in one, it actually directs the force upward and doesn't propagate from building to building, okay? So understanding what they were trying to achieve and taking the design, we redesigned the concrete so that it could be precast, okay? And you can see we got some rather strange thing. This is a beam that's actually embedded halfway into a wall. This whole system was also designed to be transported to the site and erected without any welded or bolted connections. It goes together like a tinker toy. Okay, all to be precast. Now, we were site casters at the time. Owned a company, the largest equipment in the site casting operation is, of course, a crane. We owned a crane company. We did a lot of site casting, okay? And so we bid frequently against the precasters. And normally, if the precasters were closer than we were, or closer in about 50 miles, transport cost was the deciding factor. So we got the job. We left maybe $5,000 on the table. What does that mean? If I say I left, when I bid a job, I left $5,000 on the table, what does that mean?
We've got $5,000 more.
Yeah, exactly. We could have got $5,000 more and still got the job. Okay? That was the amount between us and the next lowest bidder, which was a precaster. Okay, so the owner, the U.S. Air Force, is testing and developing this igloo type. They're going to take it out into the West Desert. They're going to build a test pattern. They're going to put one in the center. They're going to put one on all four corners of it, and then we're going to put a line of buildings out from the side. They're going to load everything with conventional explosives, and they're going to blow up the center one and see what happens. See if their design enables that explosion not to propagate. And everything is going to be highly instrumented with high-speed photography and all kinds of stuff, okay? So big liquidated damages, you don't get it ready, we got all this equipment on rent, you're going to pay through the nose, right? So they wait and they wait and they wait to issue the contract until we're into winter construction. And then we're scratching our heads saying, oh my gosh, we're planning to take all our crane and gear out into the West Desert and cast all these things. Now we got to do it in the middle of the winter. So we began to figure what else we could do, and I went and found I own the company at this point. I'm a partner with Byron Paulson Construction, okay? And so I went and I found a building in downtown Salt Lake City that was not being utilized, which was a steel fabrication company. It was a big facility. It had overhead cranes, 2 of them in a single bay, the combination of which could pick the largest piece of precast, which was 60,000 pounds. So we decided we're going to set up an operation inside the building. That makes sense in winter construction, doesn't it? Okay, but then we didn't stop from there. We said, okay, you know what? We go back into structural design and we say, you know what, we can force cure this stuff. How about if we get systems in place so that we get 2,500 PSI in 16 hours, and we create an expectation and a cycle that has to be met every day. So that's what we did. Okay, we put some sand on the floor. We cast the first floor sections that would eventually be shipped to the field. That became our base for precast construction, our casting bed in effect, okay? And because it's a long, skinny bay, we decided, well, the material's got to flow, doesn't it? It's got to come in one side, okay? All of this steel has got to be cut into pieces and welded together, and all the rebar, it's got to come in one end, it's got to be fabricated, it's got to be assembled, and then cast in where it's cast into the concrete, and then the cast pieces have to be picked and put on the trucks and sent out, right? So we began to plan all of that stuff and how it could happen and be done cheaper. Instead of forming the concrete with wood as we typically would in a site casting operation, I decided to make the forms out of stainless steel. There were 60 repetitions. I'd only have to make one form, right? And I made it so it could be assembled and disassembled with electric torque wrenches. So it was quick and easy to do. When we started to figure out where the rebar was going, we painted on the casting bed where the rebar went, color-coded it. If it was single bars. If it was a mat, we took a mat and we built one mat, and then we built all the other mats on top of it in a stack, so you can tell exactly where the rebar went from the stack below, right? Anyway, those kinds of things netted us a reduction in rebar costs for what we would have spent, probably more in winter construction, but in summer construction, we would have spent 18 cents a pound to install the rebar. Because we got the system to flow and did all of those things, our rebar cost went to 3.5 cents a pound. Our unit cost for forming was similarly reduced. It took us a month and a half before we were to this point where we had the precast ready to go, and we could do a fit-up test to make sure. See, this is what you do in a site cast situation right there. So we had enough pieces that we could do a fit-up test to make sure we would be able to meet all the dimensions and assemble this thing. So we had our forms properly fabricated. And once we had gone through that, we went into production. The plant hit 200 ton a day very quickly. You come in the morning, you'd strip the blankets. We had a boiler plant, and we had underneath the floor sections in the sand bed, we had placed PVC pipe so that it would transfer the heat from the boiler into the slab, right? So we could force cure the concrete. So in doing that, we were able to put the cylinders right in there underneath the blankets, and we had one of the men come in early in the morning. They did the brakes, took them right down to the testing lab, got the brakes so that by the time 8 o'clock rolled around in the morning, we knew whether we could pick that concrete from the slab or not. Okay? So we're stripping all of the concrete blankets off of there. We are preparing and picking all the pieces. We're setting them in piles. We're loading trucks with them. And we are cleaning the forms and the beds and doing everything to set up for that 8-hour shift so that we can pour the concrete. We do that all in the 8-hour shift with the concrete blankets on top of it, and we're on to the next cycle. Okay? So, out of an 8-month schedule, we are done in 3.5 months. All the extra overhead costs, the crane costs, the management costs, 40% job cost savings. Split between me and my partner. That convinced me that there was a whole lot of waste in this industry. Remember, we bid that leaving $5,000 on the table. And we did it with a 40% cost savings. And if we had not been forced into winter construction and gone through that process of really analyzing what could be done and how to do things faster, we'd have spent that money. At least that. And been lucky to come out with our 10% profit that we built into it. But as it was, we walked away with 40% job costs. And job profit. And I can tell you that opened my eyes to how much we were just ignoring. Just assuming that was the best that could be done, and we're not pursuing it any further. And I want to show you a video. Okay. This is in the construction. Have I shown this to you before? Okay, this is the construction of a cement plant. What you see on the ground there is a ground level assembly, pre-assembly of a conveyor section. It's going to be mounted. You'll see a picture. We'll kind of zoom out here in a minute, but you'll see a picture of there are large steel frames, we call vents, between which these conveyor sections are going to be mounted. Okay? So you've got a crusher where you bring the limestone in and you put it in the crusher. Once it's crushed, it goes on this conveyor belt. It comes up out of the pit and over into the plant where it's temporarily stored and then put through becomes clinker. It goes through the process of becoming cement. Okay? So what we're looking at here, I have been at this point, I have been on the site for roughly 2 hours, videotaping the operation that you're looking at right here. Okay? Now what they're doing is that on the top of this frame, this is a box frame, on the top of this frame between this point on this side and on the far side, this point over here, is a brace member. Okay? It's like a truss. And that brace member enables the thing to be rigid in the wind, gives it the lateral stability once it's erect. Okay? So these folks are trying to install that brace member. Now on the end of it, expand that a bit. On the end of it is a bracket that is a separate piece. It's not actually welded onto the end of the brace member. The brace member is a small I-beam, and I think it's a T-section. I don't remember. But anyway, the bracket is bolted onto the ends and then bolted into the web section of the corners. Okay? They're going to continue to try to install this all morning long. Now look at the productivity here. You can't see a fourth guy, but there's 2 guys up here, right? I have to get my electric pointer out here. Okay, so we've got this guy, we got this guy, we got that guy, we got that guy. So 4 guys plus the crane operator. We got a 5-man crew, right? So if you're out there saying, how many people are working, how many of those are working that you would say? What? Okay, is this guy working? We would define him to be working? I wouldn't say he's working. Is he necessary? Is he the guy interpreting those drawings there? Probably. But he's already done the interpretation. It's supposed to go there. That information's been transferred, right? Okay? So right now he's waiting because it doesn't go in, right? This guy is trying to look busy, do something. His job is to pre-install those brackets on the end of those things. And once they get it up here, when it doesn't fit, they're going to have to take those brackets off to install it anyway. At least one side. So is he working? Not really. Right? Okay, so let's get a little deeper. If these guys, which they do, try to install it in this bay, try to install it in the bay before that, and now they're trying to install it in this bay, are they working? They're working, aren't they? Okay? And in fact, it's really not ground level construction, is it? If they fall, it's going to hurt. Maybe a lot, right? So we haven't really got a system set up so that they're able to take much advantage of the fact that this is not in the air. Because they're in the air, right? Okay, well there's about 12 of these frames. Okay, and here goes the beam. They can't get it in here. And so, here they're going to try it still, I think, on this one. And after that, they're going to go over here, and they're going to try it in this one. And they're going to be doing that all morning long. So how productive is this operation? Not very productive, is it? Okay? Now, let's fast forward a little bit. Okay, now they're going to transfer over to the next bay, try it in that one. It's not going to fit there either. Okay, now you can see the brackets. Okay, now this is what I want to show you. Okay, now we're going to have construction manager come out on the job site. There he is. He's got out of his office. It's about mid-morning, and he comes out to observe what's going on. Because he's got to keep in touch with the troops, right? Okay? So he's going to look at that. He's going to say, okay, are they working? Well, you know, doesn't look like anything's out of the ordinary to me. It's like they're doing the best they can do, right? Everybody's working as much as they usually are. Nothing flags anything is wrong at all to this project manager. And after he stands there for a few minutes, he's going to turn around and walk right back into the office without any clue that they have not installed a single solitary beam all morning long, and neither will they until afternoon. And he is completely and utterly clueless, standing there watching. Okay, now let's talk about this a little bit, okay? Let's say we were going to improve this. Okay? Why is this beam not fitting in the first place? What could be some reason why it's not fitting? Yeah?
Temperature or something?
Okay, temperature does change things, right? And if it differentially, if it's so tight that that makes a difference, that could be a possibility. Okay, what's another option?
It's the wrong size.
Size? Okay, maybe fabricated to the wrong size, right? Okay, so how would these people know whether it's fabricated to the wrong size? What could they do to determine that instead of just trying to install? Does the erection drawing that they're working from have a shop drawing that gives the dimensions that it's supposed to be? Could they compare dimensions with that shop drawing? Okay, suppose it fits according to the shop drawing. It still doesn't fit. Why not? Is there anything wrong with the setup here? If you go to erect something, what do you have to maintain in order for the erection to continue? Are there any critical dimensions that are necessary here? Okay? Do you suppose those erection drawings provide the team with what the critical dimensions are that have to be held while they're assembling this thing to make sure that it doesn't just, relax to the point that things are moving to wherever the holes allow them to move? Okay, we're sitting on a pile. You see how there's a slope there? The ground is sloped. There's absolutely no control going on here. They just started assembling it. And as they go along, whatever the randomness of the dimensions of the holes versus the bolts are, and any dimensions that are, variance in the steel, all of that's taking a random effect here, isn't it? And in this particular case, as in most of the others, it's not going to maintain the dimensions that need to be maintained for it to be properly assembled. And so it's going to get harder, stiffer, more and more difficult to assemble as you go along. And this went way over budget and way over time. Okay, so what could we do? Do we have to just let Murphy manage our projects? You know who Murphy is, right? Everybody knows Murphy. Murphy's Law. Anything can go wrong, it will.